Vitamin C is an antioxidant nutrient involved in oxidation and reduction reactions. There are two forms of vitamin C. There is ascorbic acid and dehydroascorbic acid. So ascorbic acid is the reduced form of vitamin C and dehydroascorbic acid is the oxidized form. Vitamin C is involved in reducing free radical damage and oxidative stress. However, its ability to act as a reductant allows for its ability to reduce iron, which is a key cofactor for collagen synthesis, carnitine synthesis, tyrosine synthesis, and its metabolism. Therefore, vitamin C also plays a key role in each of these processes. There are a variety of plant-based foods that contain vitamin C. However, it is found primarily in fruits and vegetables such as citrus, tomatoes, broccoli, and bell pepper. The following slide presentation will review further details of vitamin C, including its processes of digestion and absorption, its functions as, in particular, a reducing agent, its role as an antioxidant, its DRIs, and specific deficiency symptoms. First, we will review the structure of vitamin C and the process of converting alpha-D-glucose to ascorbate. So you can see here, vitamin C, or ascorbate, also known as ascorbic acid, is actually derived from glucose. Here are the series of steps converting alpha-D-glucose all the way to L-ascorbate. Many different mammals actually have the capacity to endogenously synthesize vitamin C. They contain each of these enzymes and intermediates and therefore are able to synthesize the vitamin C from glucose. However, humans do not contain this gulonolactone oxidase and therefore are unable to synthesize vitamin C endogenously, thus making it an essential nutrient that we need to consume from outside food sources. We can see here in this diagram different versions of vitamin C. So vitamin C has both a reduced and oxidized form. And you can see here the reduced form with the hydrogens attached to the two oxygens, and then the oxidized form with the two carbonyl groups with the double bond. So the reduced form is ascorbic acid, whereas the oxidized form is called dehydroascorbic acid. We also see in the process of converting the vitamin C from the reduced to the oxidized form, there is formation of this intermediate, the semi-dehydroascorbic acid radical. To then convert vitamin C from the oxidized back to the reduced form, we have involvement of another antioxidant nutrient called glutathione. So glutathione, we're going to see later, is derived from selenium. It's a selenium-dependent compound. You see the reduced glutathione and then the oxidized glutathione. So the dehydroascorbic acid interacts with reduced glutathione. Reduced glutathione donates its hydrogens, and then the dehydroascorbic acid then becomes ascorbic acid, and the glutathione then becomes oxidized. This pattern of having two antioxidant nutrients interact to convert one from the oxidized to the reduced form, and then the other thus becoming oxidized, is a pattern that we're going to see with vitamin C. We will also see it with vitamin E, and then you also see it here occurring with glutathione. We see different food sources of vitamin C. So vitamin C is found in a number of fruits and vegetables. We see, and we typically think of vitamin C occurring in citrus fruits. Also, a good source of vitamin C is actually in red bell pepper. We see cantaloupe, lemons, some berries, and then other green vegetables also containing vitamin C. We can see that no digestion is required prior to the absorption of vitamin C. So this is somewhat unique in that no digestion will be required. We see the process of absorption of vitamin C occurs with these transporters. So we have the sodium-dependent vitamin C transporters. So we see this SVCT1 and SVCT2 being involved with the absorption of ascorbic acid. So the ascorbic acid specifically, so this reduced form, is the form that is absorbed through these transporters. We see that dehydroascorbic acid or dehydroascorbate is also absorbed through the GLUT channel 1 and 3. The primary mode of absorption is the ascorbic acid through the SVCT1 and 2. However, we do have a secondary mode with the dehydroascorbate being absorbed through GLUT1 and GLUT3. So in terms of transport, so this is referring to the transport of vitamin C in circulation once it exits the enterocyte. We see that it is transferred primarily free in plasma. Only a small amount will be in the dehydroascorbic acid form. And we also see that cellular uptake of vitamin C also occurs through the sodium-dependent vitamin C transporter as well as through GLUT channels. So not only are these involved with the absorption of vitamin C, we also see that these are involved with the cellular uptake of vitamin C. Vitamin C plays a role in a number of important processes, so we're going to see its activity as an antioxidant. However, we also see a key role of vitamin C in the synthesis of different proteins. So we see collagen synthesis it will be involved in, and we're going to talk about that process. And also we'll see it's involved in the metabolism of different amino acids. So to first discuss its role in collagen synthesis, this process and a key reaction here is a hydroxylation reaction in the synthesis of collagen. In this reaction, we see the conversion of proline to hydroxyproline and lysine to hydroxylysine, and in this reaction, iron is a cofactor for the key enzyme. So in this process, iron will need to be in the reduced state, so iron is, as the ferrous iron is the cofactor, but in the process, iron is oxidized to ferric iron. So ferrous iron is used, but then it's converted to ferric iron. So to be reconverted back to ferrous iron, vitamin C is involved as the reductant to restore iron back to the ferrous state. So we see here in the reaction, this is a key reaction in the synthesis of collagen. We see conversion of lysine to hydroxylysine and proline to hydroxyproline. We see that iron is involved in the ferrous form as a cofactor, and in the process it becomes oxidized to the ferric form. So for iron to be restored back to ferrous iron so that this pathway and this reaction can continue collagen synthesis, then vitamin C in the reduced form interacts with ferric iron to reduce ferric iron back to ferrous iron. In the process, though, vitamin C is oxidized back to dehydroascorbate. So this is how vitamin C plays a key role in collagen synthesis. It is in its ability to reduce iron back to the ferrous form so that the ferrous iron can be involved as a cofactor for collagen synthesis. We also see vitamin C involved in carnitine synthesis as well as in tyrosine synthesis and tyrosine catabolism. So we see for carnitine synthesis, it actually will function in the same way as it did for collagen synthesis. So in carnitine synthesis, we see also a hydroxylation reaction with iron as the cofactor. So in this process and in this reaction, iron becomes oxidized, and then vitamin C acts as a reductant converting the ferric iron back to the ferrous form. So we see vitamin C as the reductant converting the ferric iron back to ferrous iron. We'll see a similar mechanism in tyrosine synthesis and tyrosine catabolism. However, with some of these reactions, we see iron as a cofactor. However, in other reactions, we see copper instead as a cofactor. And you can see the oxidation states for copper are a little bit different for iron. So copper in the reduced form is 1+. Copper in the oxidized form is 2+. So instead of 2+ and 3+ for the reduced and oxidized state as we see with iron, for copper it's 1+ and 2+ instead. So for tyrosine synthesis, we have involvement of iron as a cofactor, and we learned previously that tyrosine is synthesized from phenylalanine. So to convert phenylalanine to tyrosine, we have phenylalanine monooxygenase, and the phenylalanine monooxygenase is iron dependent. So in the synthesis of tyrosine, iron acts as the cofactor. However, with the catabolism of tyrosine, in one of the reactions, copper instead is the cofactor, and we see that when copper is the cofactor, it becomes oxidized. So vitamin C is then involved in reducing copper back to the form the Cu1+. So it takes copper from the oxidized to the reduced form. Vitamin C plays a significant antioxidant role in the body, so it specifically acts as a reducing agent in the blood and within cells. It reverses oxidation, and it's in its ability to itself become oxidized that it reacts with varying nitrogen and oxygen species. This is important because free radicals attack nucleic acids, polyunsaturated fatty acids, and proteins. So when interacting with a free radical, it becomes an ascorbate ion, which then is able to be converted to dehydroascorbic acid. The dehydroascorbic acid is then reduced to ascorbic acid when interacting with other antioxidants such as glutathione. There are also reductase enzymes called reductases found in most tissues that can also convert dehydroascorbic acid back to ascorbic acid. Here we see the specific radicals that vitamin C will interact with, so it acts as a reducing agent specifically for the hydroxyl radical, the hydroperoxyl radical, superoxide radical, and peroxyl radical. So each of these it will interact with, it will reduce and eliminate its oxidative capacity. So we see vitamin C also plays a role in other potential functions. So there has been much research in its ability to prevent the common cold, also some research on its roles in reducing risk or treating certain types of cancer, and also we'll discuss its role in cardiovascular disease and also cataracts. So while a number of studies among large populations have investigated the role of vitamin C in reducing the incidence of colds, not much evidence actually supports its significant role in or influence in reducing the incidence of colds. However, some studies suggest that regular use may modestly reduce the symptoms of a cold. So it's not that if you get a cold and you take high amounts of vitamin C that it's going to reduce the symptoms or the duration, but with regular use of our intake of vitamin C, it may modestly reduce the symptoms. It does this in part by enhancing the immune response and destroying histamines that contribute to some of the symptoms of the common cold. So for the topic of cancer, some studies have indicated that an increased intake of fruits and vegetables may decrease the risk of some cancers, but this is preliminary evidence supporting the role of vitamin C. More clinical trials will need to be done. Some suggest a potential administration of vitamin C through IV infusion may also be beneficial, but this further research is needed for further support of the role in vitamin C for reducing risk of cancer. Some of the functions of vitamin C suggest that it may play a role in preventing cardiovascular disease. We know that it has an antioxidant capacity on its own or with vitamin D. It can scavenge reactive oxygen species and may inhibit LDL oxidation and decrease monocyte adhesion, which is the first step of atherogenesis. And so we see that this role in this mechanism may contribute to reduced incidence of and development of cardiovascular disease. There's also some preliminary evidence that vitamin C may reduce the risk of age-related macular degeneration and cataracts. We see here the RDA for vitamin C. So for men, it would be 90 milligrams per day. For women, it is 75 milligrams per day. We see it slightly higher in pregnancy and lactation. And smoking actually depletes vitamin C status. And so it's recommended that those who smoke regularly have slightly higher intakes, about 35 milligrams per day higher for those who smoke regularly. We see here the deficiency symptoms for vitamin C. So the main deficiency condition is called scurvy, and we see that there is an impaired synthesis of hydroxyproline and hydroxylysine, and we saw that this was involved in collagen synthesis. So these were intermediates of collagen synthesis, and so the collagen synthesis process would be impaired with vitamin C deficiency. This leads to scurvy, which has symptoms of bleeding gums and bruising, impaired wound healing, as well as these 4 H's, which stands for hemorrhagic, hyperkeratosis, hypochondriasis, and hematologic effects. Lastly, we see the UL, the tolerable upper intake level for vitamin C, is 2 grams or 2,000 milligrams per day.